everyone, and welcome to Cosmic Enigma. Have you ever looked up at the night sky and felt incredibly, impossibly small? Or what if I told you that tiny speck of light you see isn't just one star, but billions? Get ready to have your mind blown. Today, we're diving headfirst into one of the universe's most mind-bending questions. How big are galaxies? And trust me, the answer is going to make your brain do a little happy dance. Let's blast off. All right, let's start with what we know best. Our galactic home, the magnificent Milky Way. When we talk about big, the Milky Way is already a cosmic behemoth. It's classified as a barred spiral galaxy, kind of like a giant cosmic pinwheel, and its visible disk alone stretches an incredible 100,000 light-years across. Just to put that into perspective, a light-year is the distance light travels in 1 year. And light? It's fast. It can zip around Earth about 7.5 times in 1 second. So, imagine light traveling for 100,000 years just to get from one side of our galaxy to the other. That's a long commute. The Milky Way isn't just a flat disk. It has a central bulge, a halo, and spiral arms. Our solar system resides in the Orion arm, roughly 27,000 light-years from the galactic center. At the very heart of our galaxy lies a supermassive black hole, Sagittarius A star, with a mass equivalent to 4 million suns. Its immense gravity governs the orbits of stars around it. And get this, while the shining stars and gas we see make up that 100,000 light-year disk, the Milky Way's true gravitational influence, the stuff that really holds it all together, extends much, much further. We're talking about an invisible halo of dark matter that can stretch up to 2 million light-years in diameter. So when we ask how big, it's not just about what we can see, but also the mysterious, unseen forces that shape the cosmos. Our solar system? We're just chilling on one of those spiral arms, roughly halfway from the galactic center. Pretty neat, right? But here's where it gets even crazier. The Milky Way is just one flavor in the cosmic ice cream shop. Galaxies come in all shapes, and more importantly for our topic, all sizes. Each type tells a unique story about galactic evolution and the universe's grand design. First up, spiral galaxies like our Milky Way and our neighbor Andromeda. These beauties are characterized by their flat, rotating disks and those majestic spiral arms. These arms are regions of active star formation, glowing brightly with young, hot blue stars. They're the most common type, making up about 70% of all known galaxies. And they typically pack a punch with 100 billion to 400 billion stars. Imagine all those suns. Spiral galaxies are often classified further into barred spirals, like the Milky Way with a bar-shaped structure in their center, and unbarred spirals. Their disks are rich in gas and dust, providing the raw material for continuous star birth. The largest known spiral galaxy, NGC 6872, is a staggering 522,000 light-years across, more than 5 times the size of our Milky Way. Its immense size is likely due to a past interaction with a smaller galaxy. Next, we have the elliptical galaxies. These are the cosmic blobs with an ellipsoidal shape and little to no internal structure. They make up about 20% of galaxies. But here's the kicker. Ellipticals have the broadest range in size and star count. We're talking tiny dwarf ellipticals, which can be less than 10% the size of the Milky Way and contain just a few million stars. These small ellipticals are often found orbiting larger galaxies, like cosmic satellites. But then, on the other end of the spectrum, you have the absolute giants. Some supergiant ellipticals can stretch over 1 million light-years across and contain more than 10 trillion stars. These colossal galaxies are often found at the centers of galaxy clusters, having grown to immense sizes through countless mergers with smaller galaxies. A prime example is M87, a supergiant elliptical in the Virgo cluster, which spans about 120,000 light-years but contains trillions of stars and a massive black hole at its core. Another, IC 1101, is one of the largest known galaxies, with a diameter of up to 6 million light-years. So from tiny pebbles to cosmic mountains, ellipticals cover the whole spectrum. Then there are the irregular galaxies. These are the cosmic rebels, lacking any regular shape. often looking chaotic because they've probably been in a galactic fender bender or two. They're less common, around 5%, and generally contain fewer stars, typically 1 billion to 10 billion. Think of the large and small Magellanic Clouds, visible from the southern hemisphere. These are satellite galaxies of our Milky Way, and their distorted shapes are a result of our galaxy's gravitational pull. Irregular galaxies are often rich in gas and dust, leading to vigorous star formation. Their chaotic appearance provides astronomers with clues about galactic interactions and mergers, which are fundamental processes in the evolution of the universe. They are like cosmic laboratories, showing us the raw, untamed processes of galactic growth. And finally, the lenticular galaxies. These are like the awkward teenagers of the galaxy world. They have a central bulge and a disk, like spirals, but no clear spiral arms. They're also about 5% of galaxies and typically host 10 billion to 100 billion stars. Lenticulars are thought to be an intermediate stage, perhaps spirals that have used up most of their gas and dust, or ellipticals that have acquired a disk. They represent a fascinating puzzle in galactic evolution, bridging the gap between the two dominant types. And let's not forget the dwarf galaxies. These are the runts of the galaxy litter, often orbiting larger galaxies. They're typically around 10,000 light-years across. While some can have billions of stars, the ultra-faint dwarfs are truly tiny, sometimes only thousands or tens of thousands of stars. What's fascinating about these little guys is that most of their mass isn't stars at all. It's dark matter. It really shows how much of the universe's size is defined by stuff we can't even see. These tiny galaxies are believed to be the fundamental building blocks from which larger galaxies formed, offering a glimpse into the early universe. Okay, so we've talked about how big individual galaxies are. But guess what? They don't just float around by themselves. Galaxies are social creatures, gravitationally drawn together into even larger, mind-boggling structures. This hierarchical organization of matter is one of the most profound discoveries in modern cosmology. First, we have galaxy groups. These are the smallest of the large-scale structures, usually holding 100 or fewer galaxies. Our very own Milky Way is part of the local group, which includes our big neighbor, Andromeda, and over 50 other smaller galaxies. It's like our cosmic neighborhood. The local group spans about 10 million light-years across, with the Milky Way and Andromeda being the two dominant members, destined for a spectacular merger in about 4.5 billion years. This gravitational dance is a common occurrence in the universe, shaping the evolution of galaxies. Step it up a notch, and you get galaxy clusters. These are colossal structures, containing hundreds to thousands of individual galaxies. The Coma cluster, for example, stretches over 20 million light-years across and houses more than 1,000 galaxies. It's one of the most massive structures in the nearby universe, a true cosmic metropolis. And here's a wild fact. These clusters aren't just packed with galaxies. They also contain vast amounts of superheated gas, tens of millions of degrees hot, and are overwhelmingly dominated by dark matter. We're talking up to 90% of their total mass. This hot gas, known as the intra-cluster medium, emits X-rays and provides crucial evidence for the existence of dark matter. So, the biggest things in the universe are mostly made of stuff we can't even see. Mind blown. And then even bigger are superclusters. These are groupings of multiple galaxy clusters and groups. But here's a key distinction. Unlike the groups and clusters, superclusters are generally not gravitationally bound. Think of them less as a tightly knit family and more like a sprawling metropolitan area. While gravity is strong enough to hold individual galaxies and clusters together, the universe's expansion is still slowly pulling these superstructures apart. Our local group is part of the Laniakea supercluster, which means immense heaven in Hawaiian, and it spans an incredible 520 million light-years, containing the mass of 100,000 Milky Way-sized galaxies. At the most immense scales, superclusters, along with vast empty regions called voids, are arranged into an intricate, filamentary network known as the cosmic web. Within this web, galaxies form colossal walls or sheets that can span hundreds of millions, even billions of light-years. The Sloan Great Wall, for instance, stretches an astonishing 1.4 billion light-years long. It's like the universe is one giant, glowing, interconnected brain. This cosmic web is the largest known structure in the universe, a testament to the power of gravity and the initial tiny fluctuations in the early universe that grew into these magnificent structures. Okay, I know what you're thinking. My brain hurts. These numbers are too big. And you're right, truly grasping these scales is almost impossible for our human brains. But let's try some mind-bending analogies to help. These analogies are not just fun. They are essential tools for scientists and educators to convey the truly awe-inspiring scale of the cosmos. Here's one that always gets me. There are more stars in the observable universe than there are grains of sand on all the beaches on Earth. Pretty wild, right? But wait for it. Despite that, there are more atoms in a single grain of sand than there are stars in the entire observable universe. Whoa, that's a serious cosmic paradox. It highlights the incredible density of matter at the atomic level versus the vast emptiness of space. Or how about this? If our Milky Way galaxy were shrunk down to the size of a single grain of rice, about 0.5 centimeters, then the entire observable universe would be the size of planet Earth. Imagine holding the whole universe in your hands. This analogy helps us visualize the relative sizes, even if the absolute numbers remain unfathomable. And remember that light year we talked about? Light zips around Earth about 7.5 times in 1 second. But the nearest star to our Sun, Proxima Centauri, is still a daunting 4 light-years away. That means its light takes 4 years to reach us. And to cross our Milky Way, that's a cool 100,000 years for light to travel. It really puts things into perspective, doesn't it? When we look at distant galaxies, we are literally looking back in time, seeing them as they were millions or even billions of years ago. This concept is fundamental to understanding cosmology. Now, before we wrap up, let's clear up a couple of common cosmic misconceptions. Because let's be real, space is confusing. And let's also touch on how astronomers, with their ingenious methods, manage to measure these truly immense distances. Myth number 1. All galaxies are moving away from us. Well, it's true that the universe is expanding, causing most distant galaxies to recede from us. There's a huge exception. Our closest large galactic neighbor, the Andromeda galaxy, isn't moving away. It's actually hurtling towards us. Andromeda is about 2.5 million light-years away and contains a staggering trillion stars. And yes, in a few billion years, we're set for a cosmic collision. Don't worry, it'll be a slow, majestic dance, not a crash. The stars within each galaxy are so far apart that direct stellar collisions are incredibly rare. Instead, the galaxies will merge, their gas and dust clouds will interact, triggering new bursts of star formation, and eventually, they will form a new, larger elliptical galaxy, sometimes playfully called Milkomeda. Myth number 2. The universe is too big to measure. Nope. While it's undeniably vast, astronomers have developed some ingenious methods to measure its immense distances. We use something called the cosmic distance ladder. Think of it like building blocks. We use one method to measure nearby distances, then use those results to calibrate another method for even further distances, and so on. The first rungs of this ladder involve direct measurements like radar ranging to objects in our solar system. Then, for nearby stars, we use parallax, measuring the apparent shift in a star's position as Earth orbits the Sun. For greater distances within our galaxy and to nearby galaxies, we rely on standard candles, objects with known intrinsic brightness. Cepheid variable stars, for example, pulsate at a rate directly related to their luminosity. By observing their pulsation period, we can determine their true brightness, compare it to their apparent brightness, and calculate their distance. For the most distant galaxies, we use Type 1a supernovae. These are incredibly powerful stellar explosions that always reach roughly the same peak luminosity, making them excellent standard candles for measuring distances spanning hundreds of millions or even billions of light years. By observing the redshift of light from distant galaxies, the stretching of light waves due to the expansion of the universe, we can also infer their distance and the rate of cosmic expansion. These sophisticated techniques allow us to map the universe and understand its incredible scale. So, how big are galaxies? From the tiny dwarf galaxies, sometimes just thousands of light years across, to the colossal ellipticals stretching over 1,000,000 light years, and then the massive clusters and cosmic web spanning billions of light years. The universe is a place of truly unbelievable scale. It's a constant reminder of how much there is to explore and understand. Every new telescope, every new observation pushes the boundaries of our knowledge, revealing even more astonishing structures and phenomena. This journey of discovery is ongoing, driven by the curiosity of scientists and the awe of humanity. The universe is not just vast, it is dynamic, evolving, and full of mysteries waiting to be unraveled. Understanding the scale of galaxies is not just about numbers. It's about comprehending our place in this grand cosmic tapestry, inspiring us to ask bigger questions and seek deeper truths. If your mind just got a little bit blown, hit that like button. And if you want to keep exploring the cosmos with us, make sure to subscribe and ring that notification bell so you don't miss our next adventure. What cosmic topic should we tackle next? Let me know in the comments below. Thanks for watching, and keep looking up.